Hello everyone, welcome back to Math with Allison. Today we're working in our derivative series, so we're going to be talking about Newton's method. So let's go ahead and dive into it. We're going to talk about what it is. So here we have a function that I randomly drew, and what Newton's method does is it approximates the roots of a function. So the roots of the function are where it hits the x-axis is the zeros of the function. So let's go and talk about how that works. So here we have our first drawing. So here I drew a function, so that's the blue function f of x. And what we do is we pick a value that's kind of close to our zero, but not exactly our zero. So in this case, the value that we picked was x sub 0. So here we can find the corresponding tangent line, right? This right here is going to be the tangent line. And that tangent line is going to hit the x-axis. So notice it hits the x-axis right here. That is closer to our 0, which is that value of r. So it's closer to our 0 than the original point that we chose. And so what we do next is we take that corresponding x value. So we're going to take x sub 1, and now we're going to find a new tangent line. This was our x sub 0. This is our new point x sub 1, right? This is x sub 1 comma f of x sub 1. And what we do is we take the tangent line at that point, and that's going to hit the x-axis. And right here, it hits an x-axis even closer than the original 2 points because it's getting closer and closer to our r. So now what we're going to do is we're going to take that x sub 2 and we're going to take the tangent line. So remember, this was our original point that we chose that gave us this point. X sub 1 gave us this point, x sub 2, which is what we found the new tangent line for. So we can see here the tangent line, and then we can see it it's really close. It gets really, really close to r, right? So that is what this process is doing. It is taking the tangent lines each time, so that way it gets closer and closer to the root of our function. So what we're going to do is we're going to take more of an abstract general approach to it. So we're just going to say, okay, there's some point along the way, x sub n and f of x sub n, right? Those are the points that we're finding each time, but now we're leaving it general. We're not giving it an actual number. So what we're wanting to do is find the tangent line at that point, right? And the formula for a line is right here. So this is the process that we follow is we're going to plug in our x sub n and f of x sub n. So what we did right here was we took our xn and we replaced our x1, right? And then we took our f of xn and we replaced our y1. And so the purpose of this tangent line, though, is so the new y value is equal to 0. So what we do is we say, okay, well, remember, it's going to hit the x-axis close to our 0. And so we're going to say this is 0. This x value is going to be our next x sub n plus 1. So it's going to be the next number along the line, right? And so what we want to do here is we want to solve for x sub n plus 1, right? We want to solve for that next x value that we're going to find the tangent line of, blah, blah, blah. First, we distribute that first derivative, right? And then after we do that, we're going to add over that first derivative times x sub n in order to get x sub n plus 1 all by itself. And our last step that we need to do is divide by the derivative. So divide by f prime of x sub n. Here we can simplify it once, right? We can make that x sub n minus that whole thing. And here we got the formula for the next corresponding x value. So let's go ahead and talk about the procedure. Here we have it all officially written out. So we choose an initial approximation that's close to the root, not exactly equal to the root. And then for all of those n values, as you go down, you find more and more x values. We use that formula that we just found. And then we end the calculations once the result is met. So let's go ahead. That might seem really abstract right now. Let's go ahead and see a concrete example. So first, we're going to write the formula for Newton's method, and we're going to approximate x1 and x2 given our function and the corresponding x naught, x0. So let's go ahead and do this thing. First, what we want to do is we're going to be using the derivative, right, which we can see in the formula right there. So let's go ahead and just find that derivative. So f prime of x is going to be equal to, and that's going to be 2x. So let's go ahead and write our formula. So we have x of n plus 1 is equal to x of n minus, and let's go ahead and plug in x of n to our function. So that's x sub n squared minus 6 divided by, and now it's the first derivative at x sub n, so we get 2x sub n. So now we found a general formula where we can plug in any number and find the corresponding next x value. So let's go ahead and find x1 and x2 using our initial condition. And remember, our initial condition was x sub 0 is equal to 3. So here we want to find x sub 1, and this is going to be x sub 0 minus x sub 0 squared minus 6 divided by 2x sub 0. And we can plug in what that's actually equal to. So here we get 3 minus 3 squared minus 6 divided by 2 times 3. So here we end up with our x1 value being 5 halves or 2.5, however you like to look at it. And now we're going to go ahead and use that to find our x sub 2. So x sub 2 is going to be x sub 1 minus this whole thing. So let's go ahead and plug in what we have. I'm going to plug in 5 halves so I can see the fraction form. So we get 5 halves minus, and then that becomes 5 halves squared minus 6 divided by 2 times 5 halves. So this is going to be a fat algebra problem, but let's go ahead and do this thing. So we get 25 divided by 4 minus 6, but I'm going to convert that to also be over 4, so that becomes 24 over 4 divided by, and actually those 2's cancel out, so it's just 5. So let's go ahead and do the numerator. So 25 minus 24 is equal to 1/4 divided by 5, which actually we can rewrite that. So when we have a fraction divided by a whole number, we multiply the denominator by it. So that becomes 1/20. And then here we can go ahead and rewrite 5 halves to be a common denominator. So that becomes 50/20 minus 1/20. And here we get our final solution of 49 divided by 20. So here what we did was we found the formula for Newton's method. And so here is our formula. So that answers the first part of the problem. And then the second part was we wanted to find x1, which was equal to 5 halves. And we also found x2, which was equal to 49/20. I think this is more representative of what would be on an exam if calculators are not allowed. So I would assume something like this would be on an exam. If calculators are allowed, you're probably going to get a bit more of a difficult problem. So let's go ahead and try a more difficult problem. We're going to talk about Newton's method to approximate the intersection points of the pair of the curves sine of x and x divided by 2. And what we're going to go ahead and do first is graph them. So I'm going to graph in pink sine of x. And then that's going to go ahead and look something like that. So we can see here that there's going to be 3 intersection points, right? So really what we're doing here is we're setting these two equal to each other. We're taking sine of x and we're trying to find where it's equal to x divided by 2. So in order to solve for the zeros of this is we create a new function. So it's like if I subtracted over that x divided by 2, and this is equal to 0. This right here is the new function that we're trying to find zeros of. So we're going to say f of x is equal to sine of x minus x divided by 2. And here by graphing it out, we have a approximation of what those zeros are going to be, right? We know a 0 occurs right here, and right here. So what we're going to go ahead and do is I'm going to show you how to do this on Desmos. So what we're going to do is we're going to take x is equal to 0 for our first example, and we're going to go over to Desmos. Alrighty, so what we're going to do is we're going to take our function. So we have f of x, and this is equal to sine of x. So we're going to take sine of x, and we're going to subtract x divided by 2, right? So that's the function that we found. And we're going to take our corresponding x0. So in this case, we're finding the intersection points, so we're going to go ahead and guesstimate. We know that a 0 is going to occur at 0, so let's take a number kind of close to it, which I'm going to take 0.25. So here we want to do x sub 0, because this is going to be our initial point. We're going to say this is equal to 0.25. And what we're going to do is we're going to set up a formula to find the next x sub 1. In the denominator, I'm doing f prime, which represents the first derivative, of x sub 0, right? And here, but just by using Desmos, or you can do it on a calculator, we got our x sub 1. And so here we can see it's a value that's pretty close to 0. And so now I can set up x sub 2. And you do the exact same formula, but now we're subbing in x sub 1 instead of x sub 0. Okay, and then finding our x sub 2, we also get a value that's super, super close to 0. And so what this does is that it proves that this is a 0 of our function or one of the intersection points. So now what you could do is we want to find this other corresponding 0. So if I highlight it with this, that's equal to 1.89, comma 0. What you could do is you can find a value close to it. So in this case, you could choose 2, and you can set up this exact same process in order to prove that it's a 0 of the function. So I'll let you guys do that. You can also do it right here with the other corresponding 0. And remember, these two values, the zeros of this function, correspond to the function's intersection points. And so this is occurring at x equals 1.8, and then this other one corresponds to x equals negative 1.895. So like I said, you guys can set it up on a calculator, and yeah. And so let's go ahead and do one more. We have f of x equals e to the negative x, and we have x sub 0 is equal to the natural log of 2. So remember, in order to find the formula, the first thing that we have to do is find the derivative. So f prime of x is going to be negative e to the negative x minus 1. And here we can solve for x sub n plus 1, and this is going to be equal to x sub n minus f of x sub n divided by, and that's going to be the first derivative at x sub n. So let's go ahead and plug in those values. Okay, and now we're going to go ahead and find our corresponding x sub 1. So let's go ahead and do this thing. We're going to plug in x sub 0. So here, when we use exponent rules for natural logs, we have negative natural log of 2, right? That negative 1 becomes the exponent for the 2, so natural log of 2 to the negative 1, which we can rewrite as a natural log of 1/2. So let's go ahead and do that. And so the nice part about this, when you have e to the raise to the natural log, those kind of cancel out and we're just left with whatever the fraction is. So it's going to do that right here as well. Don't forget that negative 1 on the outside, but we can go ahead and rewrite this. Here we can go ahead and combine the denominator here, right? So negative 1/2 minus 1 is going to be negative 3/2. But whenever we divide by a fraction, we multiply by it flipped. So since we're subtracting a negative, that becomes a positive 2/3 times 1/2 minus the natural log of 2. And here we can go ahead and distribute that 2/3. So we get natural log of 2 plus, and that becomes 1/3 minus 2/3 natural log of 2. So we get 1/3 times the natural log of 2 plus 1/3. And that right there would be your x sub 1. And you could continue going on to find x sub 2, x sub 3, x sub 4. You could use a calculator. You could use Desmos, whatever your heart desires. So that's all I have for us today in this video. If you enjoyed it, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.